Sulphuric acid, also known as hydrogen sulfate or oil of vitriol, is a heavy, dense, oily, odorless, extremely corrosive inorganic compound containing 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms, hence its chemical formula H2SO4. Depending on its purity, sulphuric acid can be colorless and clear or dark brown. It is a strong acid, meaning it dissociates completely into ions in water. These ions are hydronium ions, H3O+, and hydrogen sulfate, HSO4-. It is completely miscible with water and is commonly supplied at a 78%, 93%, or 98% concentration. Sulphuric acid reacts readily at high temperatures with metals such as copper and has a tendency to absorb moisture and generate lots of heat in reactions. Sulphuric acid is the largest single product of the chemical industry and is purchased cheapest in bulk. No wonder it is also referred to as the king of chemicals. There are 3 distinct processes in the manufacturing of sulphuric acid. These are the contact process, the double contact process, and the lead chamber process. The contact process was developed by Peregrine Phillips, an English vinegar merchant from Bristol in 1830. After much refining over the years, this modern industrial method is preferred because it yields more product than the lead chamber process. The first step in the contact process is that elemental sulfur, pyrite, or iron sulfide, or roasting non-ferrous sulfide ore is heated with oxygen to produce sulfur dioxide. Next, the sulfur dioxide is cooled, then oxidized to form sulfur trioxide in the catalytic converter. A catalyst such as vanadium pentoxide, chemical formula V2O5, or a compound containing platinum or sodium is used to increase the rate of oxidization without affecting the yield of sulfur trioxide. The gas mixture passes over a minimum of 3 catalyst beds operating at various temperatures where the conversion occurs. This reaction is reversible. The sulfur trioxide gas is cooled to remove impurities and water vapor, which can dilute the final product. The gas is then passed through 2 ceramic packed towers where absorption with water and other liquid occurs. In tower number 1, the gas is absorbed by a stream of oleum, which is a combination of sulfur trioxide and 100% sulfuric acid. In tower number 2, the remaining gas is absorbed by a recirculating stream of 97% to 99% sulfuric acid. At this point, 98% sulfuric acid has been produced. The final product is sent to stainless steel storage tanks. It should be noted that different concentrations of sulfuric acid may be achieved by mixing and diluting. In addition, all reactions are exothermic. The released energy is converted to electrical energy, which helps operate the plant. This recycling of energy contributes to sulfuric acid's inexpensiveness. The double contact process is the same as the single contact process, but includes 2 conversion stages of sulfur dioxide to sulfur trioxide. In the first conversion, 90% to 93% of sulfur dioxide is converted to sulfur trioxide. Low temperature 98% sulfuric acid is fed through the top of the tower, and the whole mixture is heated to 80 degrees Celsius to 85 degrees Celsius. The mixture is then cooled rapidly. The mixture is returned to the absorption tower, where the remaining sulfur dioxide is converted. 6% to 9% more sulfur dioxide is oxidized, resulting in a near full conversion of sulfur dioxide gas to sulfur trioxide gas. By allowing the second conversion stage, the overall efficiency of the conversion is increased and the amount of waste gases is reduced significantly. This process is the most efficient out of the 3. The lead chamber process was developed by John Roebuck, an English physician, chemist, and inventor. The lead chamber process was first commercially used in 1746, preceding both the contact process and the double contact process. This method is not used as often today as the contact processes because it is industrially inefficient. A lot of energy is required for a very small yield. The first step involved in this process is sulfur is heated with air to produce sulfur dioxide. Next, sulfur dioxide is converted to sulfur trioxide with the use of gaseous nitrogen oxides as catalysts in a reactor called the Glover Tower. Finally, sulfur trioxide reacts with water in large box-like chambers of sheet lead to form sulfuric acid. This reaction is much slower compared to the single or double contact processes. There are many potential safety hazards when working with strong acids like this one. Sulfuric acid is an extremely corrosive acid and must be handled with care. It can easily be inhaled, swallowed, or spilled onto the body, none of which exempt the effects of acid burns. Acid burns result from the reaction of organic compounds in skin and sulfuric acid. This acid can cause severe damage to the skin, eyes, and respiratory system in the form of inflammation, burns, and/or blistering. A brittle, spongy black mass of carbon is left behind. Damage to the internal organs may be irreversible, so seek immediate medical attention upon experiencing acid burn. When conducting experiments, always add the acid to water slowly, with constant stirring to prevent explosive splattering. Sulfuric acid isn't just used to burn your enemies. It is used to manufacture fertilizers, pigments, dyes, drugs, explosives, detergents, inorganic salts and acids, petroleum refining, lead-acid storage batteries which are found in cars, glues, rayon, and films. In addition, sulfuric acid is also used in the manufacturing of chemicals such as hydrochloric acid, nitric acid, and sulfate salts. It is also used to clean gasoline and metals by washing away their impurities. And finally, sulfuric acid can be used as a catalyst and as an oxidizing or dehydrating agent in chemical reactions. Acre Solutions proprietary equipment manufacturing plant of Canada established a new facility in Pickering, Ontario in June of 2009. This company fabricates the equipment for chemical, oil, and gas industries. This includes the processing of acid coolers, gas exchangers, acid towers, acid distributors, piping systems, tanks, stainless steel converters, and heat exchangers for sulfuric acid plants. The addition of a new, larger facility in Pickering, as well as a facility in Toronto, amounts to double the production capacity. Acre Solutions is always striving to make good quality products using environmentally friendly methods of production. This is evident in the use of advanced technology and the eco-friendly design of their plant. The sulfuric acid plant within the larger Pickering facility has adopted a variety of ways to attain the green approach. This plant only uses the double contact process to produce sulfuric acid, as it reduces waste and improves efficiency. In addition, they have waste management systems, acid mist eliminators, stormwater collecting, and recycling and compost programs. There are many risks and benefits associated with the production of sulfuric acid. Some risks include the sulfur dioxide gas emissions and acid mist are contributing factors of acid precipitation, which is toxic to fish and aquatic organisms. This leads to the death of these organisms, which will affect the food chain, eliminating the predator species. Acid rain is also destructive to marble statues. Sulfuric acid reacts with calcium carbonate to produce calcium sulfate, carbon dioxide, and water. In addition, fertilizers that contain sulfuric acid may drain into freshwater lakes and trigger the rapid growth of algae, which will deplete the oxygen levels in the water and kill the surrounding organisms. And finally, burning pyrite ores leave heavy metal particles in the air, which is harmful to the environment. Some benefits of the manufacturing of sulfuric acid include that it is involved in our everyday lives, from running our cars to growing our plants and washing our clothes, so we know that the acidic pollutants aren't all for nothing. These plants are run by many workers like chemists, technicians, sales or marketing representatives, and plant operators to name a few. Sulfuric acid plants provide jobs for each type of person. These same plants are also constantly developing innovative and environmentally friendly methods for production. Some ideas include that pyrite residue that is left behind in the synthesis of sulfur and oxygen can be sent to cement and steel manufacturing factories to be used. Also, used catalysts may be solidified and properly disposed of in a landfill, and unused products can be stored or returned to the supplier. Understanding these risks and benefits can help companies decide where to build a sulfuric acid plant, biologists study organisms and their habitats, and sales representatives determine the best marketing strategies. You are now very knowledgeable about the production of sulfuric acid, but did you know that, in 2004, Canada manufactured 37,515,000 metric tons of sulfuric acid, half of which was dedicated to the making of fertilizers? Sulfuric acid is such a staple in the chemical world that there is a magazine dedicated to it. This magazine, titled Sulphuric Acid Today, exclusively covers industry and product news, mining updates, interviews with big industries, and information regarding maintenance of the sulfuric acid industry. Strangest of all, did you know that frozen sulfuric acid was discovered on one of Jupiter's moons? The intense yellow color on Europa indicates a high concentration of frozen sulfuric acid. For more information on sulfuric acid, feel free to check out these links. Thanks for watching!